All right. On day 2 of our Precal review, we're going to mainly focus on trig, solving some trig equations and stuff like that. But we are going to start out with another piecewise function. I mentioned on day 1 how important piecewise functions are to us in calculus. So that's what we're going to do here. Now we're going to go backwards. Yesterday you were given a piecewise function, you had to graph it. Today we are given a graph of a piecewise function. They want us to write it out. All right, so we'll give this a name. We'll call it f of x is equal to, we do our brace. That's how we signify a piecewise function. And then you want to put the left side of the graph on top and the right side of the graph on bottom. All right, so the left side of my graph is a linear function. So easiest way is to get it into slope-intercept form by identifying the y-intercept and another point where you can do the slope. All right, so my slope is going to be negative 1/2, rise over run, and then plus 1. And then along with that, you need to put a domain for that. So this graph is true all the way until x equals 0. So it goes from 0 to the left. So that is where x is less than, and it's a closed circle. So less than or equal to 0. All right, my other graph is a parabola in shape. That's what it looks like to me. We have a y-intercept at negative 1, and then we have a point at positive 1, 0, and then another point at 2, 3. And so this looks like if we just shifted this up 1 unit, it would be the parent function. It'd be 0, 0, 1, 1, 2, 4. And that's the parent function. So it's the parent function that's been shifted down 1 unit. X squared minus 1. And then that is going to the right of 0. So it's greater than 0. And it's not equal to because it has the open circle. I mentioned yesterday how you're not allowed to be equal to on both spots because then it wouldn't be a function because it would not pass the vertical line test at that one point. So that's it for that one. All right, now we're going to solve some trig equations. So we're going to use some of those algebra techniques. Did all of these types in Precal last year. Okay, we're going to give our answers in radians, and we're only focused on 0 to 2 pi. So you did some general form answers in Precal because there's an infinite number of solutions to any trig problem, but we're going to focus on just the base solutions, just from 0 to 2 pi, because that's the most frequent ones that we use in our class. All right, so I have a quadratic equation here, and so anytime I'm looking at a quadratic equation, I want to think about factoring. So that's what I'm going to do. Both of these have a tan x in common. So I'm going to take out a tan x. And then we're going to multiply that. We'll still have a tan x left over from this first term. And then we'll have a plus square root of 3 from that second term. And then that's equal to 0. All right. We apply the zero product property, which means that we can take our two factors and set them equal to 0 separately. And for this one, I'm going to go ahead and subtract my square root of 3 over. So I get negative square root of 3 there. All right, and then from here, we're just using our unit circle to identify where tangent is equal to 0. Remember, tangent is equal to sine over cosine. So sine, if it's equal to 0, we want the numerator to be equal to 0. So tangent's equal to 0 when sine is equal to 0. So that happens at 0, that happens at pi, that happens at 2 pi. Oh, look at this. It says just less than 2 pi, not equal to. So we do not include 2 pi, just 0 and pi there. All right, square root of 3. This, I always want to translate it to unit circle values. And so if I'm thinking sine over cosine, if I see square root of 3, then that tells me I have a square root of 3 on top and then a 1 on bottom. Now, there's not a square root of 3 and a 1 by themselves on the unit circle, but there is a square root of 3 over 2 and a 1 over 2. Okay, and then I also need this to be negative. So I either need that negative to be on top with the sine function, or I need the negative to be on bottom with the cosine function. So we want the sine and cosine to have opposite signs to get this result. All right, so sine and cosine have opposite signs in quadrant 2 and quadrant 4. All right, so we know our answers are going to be in quadrant 2 and quadrant 4. All right, so in quadrant 2, sine is square root of 3 over 2 at the pi over 3 location. So 2 pi over 3, and cosine's a half of 2 pi over 3. Then in quadrant 4, the same thing, the pi over 3 location. So it should be 5 pi over 3 there. So 4 solutions to this, and there they are. All right, next one over, cosecant x minus 2. So we're going to start by just moving that 2 over. And if you remember this one, I don't memorize my secants and cosecants. I don't even memorize the tangent ones. I always go back to sine and cosine. I have those memorized from the unit circle, so I kind of treat everything as going back to that. So I know cosecant is 1 over sine. And so you can just flip both sides over. So I can say this is sine x, and then this is equal to a half. And then I'm just something that I should know. I know sine's equal to a half at pi over 6. That's quadrant 1, and then quadrant 2. So 5 pi over 6, Q1 and Q2. And that's it. All right, C is a lot like A. It's a quadratic equation, cosine squared, cosine minus 5. This one has 3 terms, though. So this one's a more traditional factoring, where you put the 2 parentheses, set it equal to 0. So we're going to get a 2 cosine x in this first spot and a 1 cosine x in the second spot. Then I know I need to get a 1 and a 5 because they have to multiply to 5, and it has to be opposite signs, plus and minus. And then I need them to add up to negative 9. So I'm going to want my 5 to go here because 5 times 2 is 10. Then my 1 goes here. 1 times 1 is 1. And then I want the 10 to be negative because I want to end up with a negative 9, not a positive 9. So I'm going to put a minus 5 and put a plus 1. All right, then we set them equal to 0. And I'm going to go ahead and do a little bit of algebra in my head here. I'm going to subtract 1, divide by 2, so negative 1/2. And then I'm going to add 5. All right, so using our unit circle, cosine is negative in quadrant 2 and quadrant 3. And cosine is equal to a half at the pi over 3 locations. So in quadrant 2, that's 2 pi over 3. And in quadrant 3, that is 4 pi over 3. Cosine is never equal to 5. Remember that cosine is always between negative 1 and positive 1. So if you ever have cosine equal to a number smaller than negative 1 or bigger than positive 1, that is just no solution there. So we only end up with 2 possible solutions for that original quadratic equation, 2 pi over 3 and 4 pi over 3. All right, this one looks very similar to the last one, but we have one major issue, and that is that we have different trig functions here. So this one's going to require a trig identity to solve it. Okay, so we either need to try to turn everything into cosines or we need to try to turn everything into sines. It's going to be very difficult to try to turn everything into cosines because you would have to try to turn this single sine x into a cosine x somehow, and we don't have an identity that does that. What we do have is a way to turn a cosine squared into a sine squared. So I'm going to write this over to the side. You may remember this identity. This is like the most important one that you learned. Sine squared plus cosine squared is equal to 1. And so if we move that sine squared to the other side, then we have something we can substitute in for cosine squared that's in terms of sine squared, and then we're off to the races, as they say. So here we go. 2 times 1 minus sine squared x plus 3 sine x. Then I'm going to go ahead and subtract this 3 over, minus 3, to make my equation equal to 0. All right, we have a little more algebra to do. We need to distribute our 2. All right, we need to combine our like terms. Two minus 3 is negative 1. And then it's always way harder to factor if the first term's negative, so I'm just going to switch all the signs. You can think of this as multiplying everything by -1. So 2 sine squared x minus 3 sine x plus 1 is equal to 0. Okay, now we're in the same spot we were when we started problem C, where we have a quadratic equation that we can factor. So 2 sine x times 1 sine x. All right, now I need a positive 1 on the end. So it has to be a 1 and a 1, and it has to have the same sign. If I'm going to get a -3, it has to be a minus. -1 and -1. So pretty easy factoring there with that 1 on the end. All right, so that gives me two possible equations. I have sine x is equal to 1/2. We added the 1 divided by 2. And then I have sine x is equal to 1. And so this is going to be in quadrant 1 and quadrant 4. Nope, sorry. Quadrant 1 and quadrant 2, which is where sine x is positive for both of these. And so sine is equal to 1/2 at the pi over 6 locations. So that's pi over 6 and 5 pi over 6. And sine x is equal to 1 at pi over 2. And that's it. All right, next one. So we once again have a sine and a cosine in the same problem. So we need to find a way to turn one of these into the other one. Again, with the cosine x, we don't really have an identity that changes a cosine, a single cosine, into anything else. So we need to focus on that sine of 2x. This is the double angle formula. So this is just one that you need to know. This will pop up again in some of our calculus problems as well, so it's a good one to memorize. Sine of 2x is equal to 2 sine x cosine x plus cosine x is equal to 0. Okay, that may not seem like it made things easier, but it really did, because now we have two terms and they have something in common, the cosine x. So we can take out a cosine x. And that'll leave me with a 2 sine x plus 1. And now we have two factors, and we know that we can set our factors equal to 0 separately. And if I do a little algebra on this one, I get -1/2. So cosine is equal to 0 at the pi over 2 location. So that's pi over 2 and 3 pi over 2. And then sine is negative in quadrant 3 and quadrant 4. And sine is equal to 1/2 at the pi over 6 locations. So that would be 7 pi over 6 and 11 pi over 6. All right, so same idea over here with cosine of 2x. It has a different version of the formula. So I'm going to write them down. There's 3 ways to do this. So cosine of 2x is equal to cosine squared minus sine squared. All right, that would not be helpful to us because we would still have a cosine involved. And if I'm going to solve this, I need everything to be in terms of sine. So I can do something with this sine x over here. All right, so that doesn't work. Here's another way. If you applied your Pythagorean identity, cosine squared is equal to 1 minus sine squared, then you would get 1 minus sine squared minus sine squared, which would also be 1 minus 2 sine squared. All right, that's looking really good. I think we're going to use that one. Just for completion's sake, the other one is if you use that same identity on sine squared and you turn this into a 1 minus cosine squared, then it'd be -1 and then plus cosine squared. So cosine squared plus cosine squared would be 2 cosine squared minus 1. All right, so we are interested in turning everything into a sine because we have this sine x over here. So I'm going to use this one. 1 minus 2 sine squared x. I'm going to go ahead and subtract my sine x over. Is equal to 0. Okay, I'm going to rearrange, and I also want my sine squared to be a positive instead of a negative, so I'm going to switch all my signs like I did on that earlier problem. So I get 2 sine squared x plus sine x minus 1 is equal to 0. All right, now we have a quadratic, which we can factor. 2 sine x in one spot and sine x in the other. All right, -1. I know I have a 1 and a 1. Go ahead and write those in, but I have opposite signs, and I want them to add up to a positive here. So the one that's multiplying by the 2, that's the bigger number. You want that to be your positive, then your minus there. Positive 2 minus 1 is 1. All right, so we end up with sine x is equal to 1/2. And then we get sine x is equal to -1. All right, so this is in quadrant 1 and quadrant 2. And so sine x is equal to 1/2 at the pi over 6 locations. So it's pi over 6 and 5 pi over 6. And then sine is equal to -1 at 3 pi over 2. All right, now we have a half angle, which has a formula, but we actually don't need to use it. There's another way. Since there's not a sine x on the other side or some other function, we don't have to transform this into anything else. We don't need an identity here. So here's what we're going to do. We're going to divide by 2 to get the cosine of x over 2 by itself. And that's equal to the square root of 3 over 2. All right, and then whatever your angle is, so that's the x over 2, that's our angle. This is cosine of theta. Then we can use our unit circle to identify the spots where that happens. So x over 2 is equal to, and then cosine's positive in quadrant 1 and quadrant 4. And cosine's equal to the square root of 3 over 2 at the pi over 6 locations. So that's a pi over 6 and 11 pi over 6. All right, but those are not our answers because it's x over 2, it's not x. So to get your answers, you multiply by 2. So you get x, and then you get 2 pi over 6, and you get 22 pi over 6. Okay, so x equals, and 2 pi over 6 reduces to pi over 3, and 22 pi over 6 reduces to 11 pi over 3. But remember our domain. 0 is less than or equal to x, which is less than 2 pi. Okay, so pi over 3 is good to go. 11 pi over 3, though, 2 pi, if you transform that into a fraction with a 3 on bottom, that would be 6 pi over 3. So anything bigger than 6 pi over 3 is too big. So we would throw out that answer, and we would only have the single solution on this one. X is equal to pi over 3. All right, one more. So same idea here. We have the sine of 3x. There might be a triple angle formula, but I would not know what that is. But again, we don't need it because we don't have to transform the sine into anything else. It's a single sine, so we just need to isolate the sine like we did here. So I'm going to add the square root of 3. I'm going to divide by 2. All right, and then we're going to take the angle, which is our 3x, and set that equal to our unit circle values. So sine is positive in quadrant 1 and quadrant 2, and sine is equal to the square root of 3 over 2 at the pi over 3 locations. So pi over 3 and 2 pi over 3. All right, and then now we need to get x, so we're going to multiply by 1/3. 1/3 will cancel out that 3. And so 1/3 times pi over 3 is pi over 9. 1/3 times 2 pi over 3 is 2 pi over 9. All right, now it might feel like, okay, I did it, we're done, but you're not done. So I'm going to go back and talk about g here for a second. So if this was just cosine x, we would have solved it out and we would have gotten these two solutions, pi over 6 and 11 pi over 6, two answers. Okay, but since it was x over 2, it was half of x, we actually ended up only getting one answer. We got half the number of answers. Okay, and I think that's a nice way to think about it, that whatever you have in your fraction there, you're going to get you're going to get more or less answers based on that. All right, so I want to say you're going to get half the number of solutions, but it could have been like x over 3, and then we still would only end up with one solution. So it's not exactly a 1-to-1 there, but there's still something to think about, that it's going to end up eliminating at least one of your solutions. Okay, now over here, though, we had a 3x. So if we had just had an x, we would have had our two solutions, but now we have 3 times x. So we should have 3 times the amount of solutions. So instead of 2 solutions, we should have 6 solutions. So kind of weird, but here's how that works. Oops, not what I wanted to do. Let me erase this. Okay. So if I were to keep going, if I went around the unit circle one whole rotation and got back to pi over 3, so that would be pi over 3 plus, and then it would be 6 pi. We're adding 2 pi. When you go all the way around, you add 2 pi. And I want to add the over 3 version because I have a fraction. So if I add 6 pi over 3, then that would be 7 pi over 3. And if I had 2 pi over 3 and I added 6 pi over 3, then that would be 8 pi. So that's another 2 solutions right there. Now, those would not be allowed in our normal domain because they're bigger than 2 pi. But since we are multiplying by 1/3, that turns them into 7 pi over 9 and 8 pi over 9. And those are inside the domain. Those are allowed. If we turn this into an over 9 fraction right here, then 18 pi over 9 is equal to 2 pi. So anything smaller than 18 pi over 9 is allowed. So I mentioned that there were 6 solutions, 3 times the normal amount. So let's go around again. Let's add another 6 pi over 3. Okay, and that would be 13 pi over 3. And then adding 6 to 8 would be 14 pi over 3. All right, I'm going to go ahead and close those parentheses because those are it. But we will talk about going around one more time. Multiply by 1/3 and you get 13 pi over 9. That's smaller than 18, right? And 14 pi over 9. So if you went around one more rotation, you took your 13 pi over 3 and you added 6 pi over 3, that would be 19 pi over 3. 19 numerator, even if you multiply it by 1/3, you get 19 pi over 9, which is bigger than 18 pi over 9. So that's how you know that you're done. All right. Hope you love trig as much as I do and you enjoyed this video. Good luck on worksheet number 2 for your homework.